Good evening, everyone. So this is Fluidization Engineering NPTEL course live interaction session. So we'll start the session by 6:05 sharply. We'll wait for a few more participants to join if ever.
Can you share the previous class recording? I wasn't there actually adding that.
Yeah, actually, NPTEL will share the link for those session. So
Actually, I didn't get it. So, you like share it
I mean,
on the
they
portal?
yeah. It is recording is there. It will be like open to all only. Like, did they share some Excel sheet link
No, no, they didn't share anything.
through? Okay, okay. I'll just see. Yeah.
Yeah, thank you.
So good evening, everyone. This is the live interaction session 2 for the NPTEL course Fluidization Engineering. The course instructor is Professor Subrata Majumder from the Department of Chemical Engineering, IIT Guwahati, and the live interaction session is handled by Ankara Kartiga from a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So the session takes place every Friday between 6 p.m. and 8 p.m. for the duration of the course. So we'll just start with it. So in the last class itself, we have seen about the course layout, like how it is planned for the course to be going from the weeks 1 to 12, since it is the 12-week course. Fluidization itself is a separate is handled as a separate subject, and it is modeled for the 12 weeks. So the syllabus will be covered by the course instructor, and the videos for the same will be uploaded in the NPTEL website. These problem solving sessions are just here to aid you in solving those problems or the solving the assignments, or if you have any doubts associated with the original content, the original lecture content from the professor, you can ask here. um, so basically, in the course, uh, it is in the first two weeks. The course is about introduction to the phenomenon of fluidization, and the theory behind it, and including the advantages and disadvantages of fluidized bed and where all it is used in the industries, like whichever the application that is focusing on the focusing on particulate flows with fluidization technology. And in week from the week 3, it is basically focusing on the characterization of solids and the flow characteristics, and its outline different types of fluidization. So basically, fluidization is a phenomena, and in with varying the velocity of the fluid, there would be different regimes of fluidization, which we would be seeing in the further classes. And in the weeks 4 to 5, we would be dealing with the flow patterns inside the fluidization system, and the flow pattern transition, frictional pressure drop and its model to analyze, and also the solid movements. Basically, fluidized beds can be used for mixing operation or segregation operation. It can be done through the variation of the velocity of the fluid that is passing through them. And in the week 6, it is for focusing on the gas distributor and types of gas distributor in the small scale and large scale industries, and how to design them. Followed by the study of bubbling fluidized beds and the gas dispersion and the gas interaction in the bubbling beds and the mixing characteristics for the same. And in week 8, we will be dealing with entrainment and elucidation from the fluidized beds. And week 9, it is attrition mechanism and its model by and its analysis by model. And week 10 to 12, we will be basically dealing with the mass transfer phenomena and the heat transfer phenomena associate taking place inside the fluidized bed. The fluidized bed is mainly very found very useful in terms of its mass transfer and heat transfer properties, because in packed bed there are chances for hotspots to form when we are dealing with the highly exothermic reaction, which can be which can be minimized when we are using fluidized bed reactors. So its heat transfer phenomena plays a major role, and followed by the design of the fluidized bed reactors, like based on the different types of reactions. So if it is catalytic reactor or non-catalytic reactor, depending on it, the design for the same would be studied in those classes. So this live interaction session would be dealing with the problems, uh, focusing on the week's content, and that would be dealing with few sample problems. And once the assignment submission deadline is over, if you people are having any queries regarding the assignments that are submitted, you can ask here. We can solve those problems also. Till the submission deadline is not met, those problems would not be discussed here. So these are the course layout, and we have discussed what we would be doing in the course duration, and the reference books for the course is given over here. The main book that would be dealing with all aspects of fluidization is Fluidization Engineering by Cooney and Levenspiel. And this book basically covers all important aspects, all the basic information that we people need to know before going, while studying fluidization. So this book covers almost all the things required as a basics to understand the phenomenon of fluidization. So it is a very good book. And this one, Gidaspo, multiphase flow and fluidization, continuum and kinetic theory description. So this one is a book that is focusing on the basics of fluidization with further focus on the modeling aspects also. Like for example, in fluidized bed we have a particle system and the fluid is passing through it. So continuum or kinetic theory description necessarily means that the particles that are in the fluidized bed, those particles would also be, instead of tracking those particles as an individual entity, we would be assuming it to behave as a continuum. Like in that aspect, the models would be modified and it would be dealt in the modeling aspect. So that modeling aspect is also covered in this book, but it is not necessary at this level of course. So just for your information. And the third one is the Giblero fluidization dynamics. And the last one is the professor's hydrodynamic and transport process of inverse bubbly flow. So these are the books and references for this course. So now we'll just, before moving into the problems, we'll just have a quick recap of fluidization phenomena. This one we already saw in the last class, but for getting a quicker grasp of the concept, we'll just go through the concepts one more time. So what is fluidization? Fluidization is a phenomena in which we pass the fluid, here we are passing air, into the bed. So this air would be passed at a very high velocity so that the drag on the particles is exceeding the gravitational pull of the particles. That is, for example, consider this bed. Here we are packing the, in this is considered it as a packed bed. Here the particles are packed till this level from here. So inside this, when we pass the fluid at a very low velocity, the particles would be experiencing some drag force because of the fluid that is flowing from here. But that drag force would be very low, so compared to the gravitational force. So since gravitational force of the particle is very high, the particles would not be moving, they would be they would be packed, they would be remain in the packed condition itself. So this is known as packed bed. But once when we pass the fluid at a very high velocity, that is, we have a condition known as minimum fluidization velocity. All these would be studied in the flow of the course. So at minimum fluidization velocity, that is when, I mean, we keep on increasing the velocity, there is a point comes when the drag of the particles is balanced by the gravitational force. So the particles remain suspended in the fluid. They would not be remain in the packed condition, but rather they would remain suspended in the fluid, but it would not be moving. So this in a kind of in a loose packed manner. So at that point, it is known as minimum fluidization condition, where the particles are becoming very loose. The weight of the particulate system, that is a fluid and the particle, is balanced by the gravitational pull. So this is known as minimum fluidization condition. Once the minimum fluidization condition is surpassed, that is after which we keep on increasing the fluid velocity, what happens is that the particle starts moving. The particle starts moving, and it would, consider this is the packed bed height. At minimum fluidization velocity, it would be kind of more. Once it the after minimum fluidization velocity, how much ever we increase the fluid velocity, the particle starts going upwards, and it kind of moves up. So this point is known as, I mean, this is a fluidized bed condition. There are various regimes associated with this, but in general, it is a fluidized bed. The particle starts moving and it behaves as a fluid. That is known as fluidized bed. So this, why do we go for fluidized bed? Because since 1920, fluidized bed is commercially being used in the industries. uh, be, there are certain disadvantages too when we are dealing with fluidized bed. For example, the design of the system is very complex, and building and operating the system is also complex. When we are considering the scale up of this to industry level, again it is difficult, and also there are certain disadvantages associated with the particles. For example, since we are passing the air and the particle starts moving, the particles are nothing but they would be catalyst for the catalytic reactions and so on, like depending on our need. So at that point, consider the particles moving against each other. So there would be attrition, erosion, and they also would be moving against the walls. So there are high chances of the particles to become distorted because of the phenomena happening like attrition and erosion and all against the walls and against the particle interaction itself. Particle wall or the particle interaction. So, all considering all these, there are various disadvantages associated with the fluidized bed. But then, why are we going for the fluidized bed? Because as I already mentioned when we were discussing about the heat transfer, in the heat transfer that is mechanism happening inside the fluidized bed is very superior. For example, since the particles are moving keeps on moving, the heat transfer rate is very higher. I mean, heat transfer rate is higher than the reaction happening inside the packed bed. And also the solids move like a fluid, and it is very easier to deal with particles when there are like various size distribution rather than a single size. For in industries, when we are dealing with, it would not be constituting a single size particles, rather they would be dealing with a quite range of particles with different size distributions. So when dealing with all those things, it is quite easier when we are going with fluidized bed rather than the packed bed. Also, it is since the heat transfer rate is made quite higher here, the isothermal profile is easier to maintain over this rather than in packed bed. Also, think about it, like here the solids keep on moving. So when the in catalytic reactions, uh, once the catalyst is like use spent or used up, we need to regenerate it, or I mean we need to recycle those catalysts, right? For that we need to move the catalyst, and we need to recycle it separately. If we are dealing with the packed bed, consider it would be very difficult when we are operating it at the industrial scale. That is, the particles would be over here, and we need to be removing it and recycling it and regenerating it. It is a quite hectic task. But when we are dealing with the fluidized bed, since air is passing over here, the particles would be easily, like depending on the velocity, the particles can be easily moved over, and it can be collected and regenerated, and it can be passed over here. This is the principle used in FCC, fluid catalytic cracking. So all these things are made possible only when we are dealing with the fluidized bed. So this makes it, all these advantages are enormous, that it like suppresses the disadvantages associated with this bed and makes it a useful thing, that it considers, that it can be considered as a useful reactor in the chemical engineering industries. When we are dealing with, it depends on application also, but it has more advantages than the disadvantages. So yeah, now, yeah.
A couple of limitations with fluidized bed, right? So
Hmm.
can you use like gel-based packing in order to avoid things like
Or like it depends on the particles, right? We cannot. What do you
like
mean by gel based?
gel-based? Okay, say you're using a catalyst, nano catalyst, whatever. You can disperse in a gel, make it in the form of spheres or whatever packing, and then disperse it so that you know the property of gel, right? Attrition is minimum, and like whatever disadvantages are like overlooked.
Yeah, like if the reaction condition doesn't affect, it can be done. Like, and the airflow doesn't affect.
Yeah, and even they're light also.
What?
They're even lightweight as well.
Yeah, okay. Yeah, it depends if the fluid flow does not, it is not affected, and the reaction catalyst is not affected, it can be done. But it is not like, in few conditions it can be done depending on the need. It is, yeah, it can be done, but yeah, depends on what purpose we are using, and if it does not affect the condition, we can go for it. Like for all the reactions or all the condition, all the applications, it is not always suitable. Yeah. So yeah, uh, so in the previous slide we were discussing about the air velocity. that is the fluid velocity which we are passing inside the fluid. So with increase in the fluid velocity, how the pressure drop is varying and what is minimum fluidization velocity. So what happens is that when we are passing the fluid inside the bed, the particle like the particle becomes it has the upward flowing gas, so it experiences some drag force. The drag force is nothing but it is a friction imposed by the incoming fluid on the particles. So because of those drag force, till a certain point it would be very low, like consider here, when till this point the drag force would be very low compared to the gravitational pull. So because of which the particles remains in the packed bed condition or the fixed bed condition. So what happens to the pressure drop is that the pressure drop would keep on increasing till the fixed bed, till the point of fixed bed, because I mean it keeps on increasing till we go for the fixed bed. Once the fixed bed condition, I mean once the minimum fluidization is condition is met, the weight of the fluid and the particle would be equal to the gravitational pull at the I mean the weight would be equal to the drag force. So therefore at this point this is known as minimum fluidization. So the velocity at this point is known as minimum fluidization velocity, after which the solids inside the packed bed, they would be starting to move. So because of which the pressure drop remains the constant. Like there would be no further need required to move the particles, because it would be weight of the particles per the area. So the pressure drop remains a constant once the minimum fluidization condition is met, after which the particles starts to behave as a fluidized bed. So after this point the pressure drop remains a constant. So pressure drop keeps on increasing till the point till the some velocity. This velocity is known as minimum fluidization velocity, and this can be calculated by using various equations like Egan's equation, Venn and U equation, and depending on the there are so many equations and with some conditions imposed on them. But for the spherical particles in fluidized bed, there are various correlations available to find out the minimum fluidization velocity. This is known as UMF. And before UMF, the bed starts behaving as a fixed bed, and after which the bed starts to behave as the fluidized bed. So these are all the different regimes of fluidization which would be studied in the further classes. And yeah, I mean this one is the fluidization regimes, like depending on the fluid velocity, how the bed starts to behave is shown over here. For example, as we have seen in this, when the gas velocity or the fluid velocity is very low, what happens is that the bed remains as the fixed bed. There would be no provision for the bed to move, I mean the particles to move. So this is known as fixed bed. So once I mean this is with increasing in the fluid velocity. So from A to H we are increasing the fluid velocity. With further increase in the fluid velocity, we can observe that the particles are kind of loosely packed, that is they are suspended in the fluid medium but they are not starting to move. This point is the point where the particles are suspended in the fluid medium is known as minimum fluidization. So this is given by LMF. And for
Does the minimum fluidization depend on length and volume of packing?
I mean
The
minimum
minimum
fluidization,
fluidization does the minimum fluidization velocity depend on the length and volume of the packing?
I mean it is, I mean it does not depend on that, but in turn it affects the length and the volume of the packing. I mean, but in the initial packing conditions, void fraction or the volume fraction, that affects the minimum fluidization velocity.
Take two cases, one where we have like 1 meter length of packing and 2 meter length of packing. So
Okay.
like when you do the fluidization for both the cases, minimum fluidization velocity, will it be the same or will it vary in both the cases?
If the packing fraction is the same, it would be, I mean,
Same.
it would be the same, yeah. And yeah, one second. Just a minute. Yeah. So after minimum fluidization velocity, I mean minimum fluidization condition is met, there are we can say two types of fluidization depending on the fluid medium. Like one is liquid and the other is gas. So for the liquid case, what happens is that if with further increase in the fluid velocity, the particle starts to expand, and this is known as smooth fluidization because the particle bed starts to move, but it would be kind of smooth as shown in this figure. But if when we are dealing with the gas as a fluid, bubble starts to form inside the fluidized bed, and because of this bubbling fluidization, I mean, because of this, the bubbles initially it would be smaller bubbles, and the bubble size keeps on growing. So, depending on the bubbles, in turn, slightly affect the mass transfer happening between the particles and the fluid. So, it is kind depending on the application wise, the bubbling fluidization is understood. But once with in the liquid case, however, the bubbling is not observed in most cases. So this is known as smooth fluidization when we are dealing with the liquid, and when we are dealing with the gas, it is bubbling fluidization. With further increase in the gas velocity, the bubble starts to grow in size, and once the bubbles almost reaches the 3/4 size of the diameter of the column, this is known as, I mean, slugging happens. That is where the bubbles grow almost 3/4 of the size of the column. This is known as axial slugs. With further increase in the gas velocity, the bubbles in turn grow in size, and it almost reaches the size of the column as shown over here. This is known as axial slugs, and this is known as flat slugs. These are just happening when we increase the fluid velocity, that is gas here. But in turn, we can observe that with further increase in the gas velocity, the bubbles are very like forming very and more number of bubbles are getting formed, and they go over the top, and here the bubbles would burst, and the particles that is carried along with the bubbles would be thrown out, and there would be a turbulent regime happening over here, and this is known as turbulent fluidization. At last, what happens is that with further very high velocity of gas or liquid, the particles would be transported to the top, that is known as lean phase fluidization, where you can see here this much packing was initially there, and only these many particles are over here. All the particles will be evenly distributed till the top of the column, and this is known as lean fluidization or pneumatic transport. This phase is very useful when we are dealing with the transport of the particles, and so at this point it is known as lean phase fluidization. For this, what we can do is we can take the particles out separately, and we can recycle it back at the bottom. So like depending on the purpose and the application, the particles can be trapped from the top and removed from the top, and it can be put it over at the bottom for the lean phase fluidization or the pneumatic transport. So these are the fluidization regimes that we are covering when with increase in the fluid velocity from the very low velocity to the very high velocity. So next aspect is that not all particles behave the same inside the fluidized bed. For example, there are larger size particles and there are smaller size particles. So depending on the particle size and the particle density, the particles would be behaving differently inside the fluidized bed. So since to understand that concept of how the particles are behaving inside the fluidized bed, Geldart gave the classification of the particles into 4 categories: A, B, C and D. So the very low particles, smallest particles comes under the Geldart C particles. These particles are having very small diameter, and these are nothing but giving rho p minus rho g. There is particle diameter minus the particle density minus the fluid density in the y-axis, and the particles mean average diameter in the x-axis. So For the very smallest particles, they fall under the gel.c particles or the cohesive particles, gel.c. In gel.c particles, they are very smaller particles, so they will be very cohesive in nature. These particles are very difficult to fluidize, because imagine when we are fluidizing very smaller particles, the chances of them sticking to each other is very high. So it is not easier to fluidize them or easier to move, and they would stick together and channels would be formed for the fluid. So the proper transfer of the, mass transfer between the fluid and the solid phase would not be happening in the gel.c particles. So the appropriate condition should be met when we are dealing with the gel.c. Next is the gel.a particle. These are comparatively larger in size than the gel.c particles, but still they are smaller. And it is easier to fluidize the gel.a particle. It is comparatively easier to fluidize gel.a particles because they are somewhat larger in size, and also the so because of that, what happens is that it is it leads to smooth fluidization. Bubbles would not be formed till a certain point in time. Only after that point condition is met, bubbles would be forming. So it is one of the favorable condition when we are dealing with the fluidization. And the further larger size particles and heavier particles in terms of density is the gel B particles. They are sand like. What happens is that these fluidization, fluidization of gel B leads to quicker formation of bubbles. So controlling the bubbles inside the fluidized bed is quite difficult. So it is again in turn preferable in most industrial conditions, but the bubbles would be formed which should be dealt accordingly. And the last one is the gel.d particles or the spoutable particles. In gel.d in this type of fluidization, it is quite difficult. The larger bubbles would be formed when we are dealing with the fluidization of gel.d particles. So it is quite difficult for fluidizing gel.d, but it can be used in spoutable beds, where it is in spoutable beds. What we do is we pass the fluid only at the center point, not uniformly. So at that condition, it is preferable to use for those, it is preferable to use gel.d particles. So with this, we just move on to see few problems for this, few sample problems, and then we'll discuss the solution for the same. So the question one is, at the terminal velocity, the weight of the object is weight is equal to buoyancy force plus drag force, or the weight is greater than drag force, and or the weight is less than the buoyancy force plus drag force, or option D, it is none of the above. So answer is, at the terminal velocity, what happens is that it is the weight of the particle is balanced by the buoyancy force plus the drag force of the particles. This one we saw in that like at the terminal velocity, once the terminal velocity is reached, the particles would be like it would be transported easily. But at the point of the terminal velocity, the weight would be equal to the buoyancy force acting on the particle and the drag force acting on the particle. So weight W, that is the weight of the object, is equal to the buoyancy force plus the drag force. So this is question 1. So actually, at some speed, the drag or the force of the resistance will be equal to the gravitational pull on the object. At this point, the object stops accelerating and continues falling at a constant speed called the terminal velocity. So when the drag force and the gravitational force together, drag force is balanced by the gravitational force, this point is known as the terminal velocity. So this is what we have seen here. And the buoyancy force and
Same as minimum fluidization velocity.
yeah, kind of. It depends, but conceptual wise, it is. So this is question 2. When the packed bed condition diminishes, the frictional pressure drop can be estimated by using so Fick's law, Ergun's equation, Stokes law, and Newton's law. So when the once the packed bed condition is surpassed, that is once the fluidized bed is starting to behave, to measure the pressure drop of those bed, we use the Ergon's equation. Ergon's equation is given by this, where delta P is given by, this is for the in general this is for the laminar equation and laminar condition, and this is for the turbulent condition. But together, when put together, we get the pressure drop equation for the fluidized bed, and this is known as Ergon's equation, where this is 150 mu u naught LB 1 minus epsilon the whole square by epsilon cube by 5s square dp square plus 1.75 rho u naught square LB plus into 1 minus epsilon by 5s dp into epsilon cube. This mu is the fluid viscosity, and u naught is the superficial fluid gas velocity or the liquid velocity, and this is the length of the bed, and epsilon is the packing fraction, sorry, it is the void fraction inside the bed, and dp is the average diameter of the particle, and 1.75 is 1.75 rho density of the fluid, and again 5s is the sphericity of the particles inside the system. Once again,
What is mu and mu naught? Could you repeat?
mu is fluid viscosity, u naught is the fluid velocity, and so answer is Ergon's equation, that is option B. And now we'll just go to question 3. For spherical particle, sorry, in this it is epsilon is the void fraction. Yeah. So for spherical particles, the minimum voidage of the bed is usually in the ranges of 0.4 to 0.45, 0.5 to 0.55, 0.6 to 0.65, 0.7 to 0.75. When we are packing the particles inside the bed, we can do random packing or structured packing. So it can be, when we are dealing with the structured packing, it can be squared packing or hexagonal packing, and depends. But in general, the condition is such that the packing fraction is higher when we are dealing with the spherical particles. So if the packing fraction is higher, it means that the voidage would be minimum. Like so it in the for the proper packing condition, the sphere's packing condition would be between 0.6 to 0.7 at that case of closed packing or very tight packing. So we all know that at minimum voidage of the bed, that is minimum fluidization, like it is the starting of the fluidization, that is minimum fluidization condition, the particles would be suspended in the air. So it would not be between 0.7, that is 0.7 means it would be 0.3. So it would be somewhat more than 0.3, but it would be very less compared to all the other things. So the answer to this is 0.4 to 0.5. So answer is option A, that is 0.4 to 0.55 for the spherical particles. For the non-spherical particles, again this would be increasing because the packing fraction of the non-spherical particles are comparatively lesser than the spherical particles. So the answer is, for the spherical particles, minimum voidage is 0.4 to 0.45. And okay, for this is question 4. The minimum fluidization velocity is affected by the factors, that is option, this one is the Ergon's equation, from which this can also be used to determine the this can be used to determine the pressure drop. But in terms of pressure drop, if we put that rho g h and we get the if we solve for the u naught, at that point it would be umf, we can get the minimum fluidization velocity. So what affects the minimum fluidization velocity is that bed diameter, particle size, and the fluid density. So actually all of these affects the minimum fluidization velocity, because it would be fluid density is there, and particle size is also there, and bed diameter would again influence the packing of the particles. So the answer to this is all the above. So we'll just move on to question 5. Buoyancy force experienced by a submerged solid particle is equivalent to volume of the fluid displaced by particle volume into fluid density into gravitational acceleration, and it is weight of the fluid displaced by the particle volume into fluid density into gravitational acceleration. Option C, it is both A and B. and option D, it is none of the above. So it is buoyancy force is that when we are suspending the particles inside the fluid, the force experienced by the particle is the buoyancy force. So like it is the tendency to the object when it is floating in the fluid. So it is given by rho gv in general. So on seeing that it is rho is common in both of them, that is fluid density, and gravitational acceleration is again here, that is rho into g is there, and it is into v. So volume of the fluid displaced by the particle volume. So answer to this option A. Option A, volume of fluid displaced by the particle volume into fluid density into into gravitational acceleration. So now we'll see the question 6. At the minimum fluidization velocity inside a fluidized bed, all the particles are just suspended by the upward flowing gas or liquid, and the frictional force between particle and the fluid counterbalances the weight of the particles, both A and B, or option D, it is none of the above. So we know that at the condition of the minimum fluidization, the particles would be suspended in the fluid medium when the fluid is passing up, like at the condition of upward flowing gas or liquid. So option A is true, and option B, it is given that the frictional force between the particle and the fluid counterbalances the weight of the particle. So this is also true, right? When the frictional force between the particle and the fluid, that is the drag force, is equal to the weight, a gravitational pull, that is the weight of the particles. So both option A and B is the right answer, which is given by option C. At the minimum fluidization velocity inside a fluidized bed, all the particles are just suspended by the upward flowing gas or liquid. And option B, the frictional force between particle and the fluid counterbalances the weight of the particles. So answer is option C, both A and B. Okay. So drag coefficient in the turbulent flow regime is equivalent to 0.44 when the particle Reynolds number is REP is greater than 500, REP is greater than 1000, REP is greater than 1500, or REP is greater than 2000. So what happens is that the drag coefficient, it varies depending on the flow regime, that is if it is turbulent or if it is laminar. In laminar it would be depending on the equation would be got from the Stokes law, whereas here in the turbulent regime mostly it is equivalent to 0.44 for the spherical particles. So at when we associate the turbulent flow regime depending on the Reynolds number, for example in the flow through a normal cylindrical pipe, we have the Reynolds number would be less if it is 1000, and if it is less than 1000 we have the it to be a laminar regime, and if it is something it would be turbulent. But for the condition of packed bed or in the fluidized bed, what is the equivalent Reynolds number to identify the turbulent flow regime? The answer is option A. But what is the condition when it is laminar regime or the like for laminar regime, how the value would change is, for if the Reynolds number of the particle, that REP is basically given by REP, that is Reynolds particle Reynolds number, it is equal to rho fluid G dp, that is the diameter of the particle, divided by mu f. This is the particle Reynolds number. So in general condition, what we do is, if it is a flow through a cylinder pipe, we use the diameter of the pipe, right? So that is flow Reynolds number. Here the particle Reynolds number is given by rho g dp by mu, where dp is the diameter of the particle, rho is the fluid density, and g is acceleration due to gravity, and mu f. So if rep is less than 1, we associate it with the laminar regime. So it is Stokes flow. The laminar regime is for rep less than 1. If rep is between 1 and 500, it is a turbulent regime. Sorry, not turbulent, transition regime between laminar and the turbulent. And if rep is greater than 500 and less than 2 lakh, this is known as turbulent regime, where the drag coefficient is equivalent to 0.44. So at this since this criteria, like generally it is exceeding 500, we associate it as turbulent flow regime. So depending on the regime, the calculation formula, like in terms of terminal velocity, everything varies. So it is an important parameter, I mean, to identify the flow pattern or flow regime for the in case of fluidized bed or the packed bed. So we'll go to the question 8. This is the value REP is greater than 500. And now we'll go to question 8. In question 8, it is asked that at the onset of fluidization, the voidage is larger than in a packed bed, smaller than in a packed bed, equivalent to that in a packed bed, or option D, it is none of the above. What happens is that at the onset of fluidization, that is we here itself we saw in the diagram, like this is the onset of fluidization, this is the packing fraction, and this is the packing fraction for this. So from here it can be seen that the voidage in this, that is consider, we'll keep it as epsilon m, and here we'll keep it as epsilon mf. So the voidage is more here, voidage is lesser here. So what does it mean is that at the onset of fluidization, or even here, the voidage is very high. I mean, we'll keep it M and we'll keep F here. Fixed bed, and this is normal bed. Yeah. Whatever. The voidage keeps on increasing with the increase of the fluid velocity. So this is the onset of fluidization. At this point, however, the the voidage in the bed is very higher than the than that at the fixed bed condition. So at the onset of fluidization, the voidage is larger than in a packed bed, smaller than in a packed bed, equivalent to that in a packed bed, none of the above. So the answer to this problem is question 8. Option A is the right answer. That is larger than that in a packed bed. So yeah, answer is larger than in a packed bed. So the question 9, it is about Archimedes number or Galileo number is proportional to diameter of the particles, square of the diameter of the particles, cube of the diameter of the particles, and none of the above. So Archimedes number, it is used just to identify, I mean, it is one aspect used to identify the calculate the minimum fluidization velocity. So the Archimedes number is here, it is given by general Archimedes number is G L cube rho L, that is rho liquid, into rho P minus rho L by mu square. Rho L is the density of the fluid, that is liquid, given over here, and rho L is the density of the fluid, and rho P that or rho is the density of the particles, and g is the acceleration due to gravity, and L is the characteristic length of the concerned in the application, and mu is the viscosity of the fluid. Since we are dealing with the particle flow over here, L should be dp in this. So Archimedes number is equivalent to g dp cube rho L into rho P minus rho L by mu square. So since it is proportional to dp cube, Archimedes number or Galileo number is proportional to diameter of the particles, square of the diameter of the particles, cube of the diameter of the particles, or none of the above. Answer to this question is option C, that is cube of the diameter of the particles. So our answer is option C, that is cube of the diameter of the particles, that is g dp cube. So since L is the characteristic length, here we are associating with the particulate fluid L or dp, both are just the same. So it is, since it is proportional to cube, the answer is cube of the diameter of the particles. Okay, at the minimum fluidization velocity, at the minimum fluidized condition, the pressure drop through any section of the bed is equivalent to weight of the fluid in that section, weight of the particles in that section, weight of the fluid and the particles in that section, all the above. So what happens is that at the minimum fluidized condition, we vary the fluid velocity, and we at one point we reach the minimum fluidized condition where the particles would be suspended in the bed. So the pressure drop is equivalent to the particles suspended in the fluid, that is fluid together with the particles, that or the particles together with the fluid, that weight is equal to the pressure drop. So the answer to this question is option C, that is at weight of the fluid and the particles in that section. Actually the question asks, at the minimum fluidized condition, the pressure drop through any section of the bed is equal to the weight of the fluid and the particles in that section, that is option C. Yeah, option C is the correct answer, weight of the fluid and the particles in that section. So yeah, the time is now 6:55. We'll just take a 5 minutes break and we'll just start by 7 p.m. Yeah, we'll resume the session. So actually, before I forget, in last week problem, actually there was a question where it was about what happens with the increase in the fluid velocity in terms of the question was that, and the options given were with increase in the fluid velocity the pressure drop increases and the uniform distribution would be there. So in that question the answer was option C, that is both A and B, not none of the above. Sorry for the confusion, I'll just put the question again in the next class. But the with increase in the fluid velocity before till in terms of before the fluidization, it pressure drop would be increasing and the gas velocity would also increase. So that was the confusion from the last class. So now we'll just go with this week's problem. Okay. uh, the gas holdup can be experimentally obtained by the phase isolation technique, where alpha g can be estimated by ratio of gas volume to the mixture volume, ratio of liquid volume to the mixture volume, ratio of gas volume to the liquid volume, and none of the above. Okay, alpha G here is the gas holdup or the gas fraction in that system. So it can be experimentally determined by phase isolation technique. So the question is not about the techniques and all. How to determine the alpha G, that is gas holdup. So consider the consider the system where we have gas, liquid, and solid. Each have its own volume fraction, that I mean volume of gas, volume of liquid, volume of S, and together it everything put together we get the volume of the mixture. So how do we determine the volume fraction of the gas fraction, gas holdup or something? We go with the volume of the gas by the volume of mixture divided by the volume of mixture gives the gas holdup or the gas fraction. So here in this context it is the gas volume to the mixture volume. This is the right answer. This is ratio of liquid volume to mixture volume. This is the liquid holdup. Alpha L or liquid holdup. Liquid holdup. And this is ratio of gas volume to the liquid volume. It does not denote anything in this context. So the alpha G is determined by the gas volume to the mixture volume. So the answer to this question is option A. We'll see the answer is ratio of gas volume to the mixture volume. And now we'll go to question 12. Okay. Terminal velocity ut can be found from balancing the forces gravitational force and inertial force per unit volume of the particle. Okay. Gravitational force, buoyancy force, and drag force per unit volume of the particle. Gravitational and drag force per unit volume of the particle. So terminal velocity, when we are calculating, it is for the particle, right? So it is similar to the calculation during minimum fluidization velocity, but it is calculated for a single particle. So what are all the forces in general that would be acting on the particle? That is gravitational pull that is acting downwards the particle, and the buoyancy force and the drag force acting pulling the particle. So we need to balance all the particles in order to determine the terminal velocity. So the answer is option B, that is we need to balance the gravitational force, buoyancy force, and the drag force per unit volume of the particle. Only on balancing all the forces we can get the terminal velocity. So the answer to this problem, that is question 12, is option B, gravitational, buoyancy, and drag forces per unit volume of the particle. Answer is option B, gravitational, buoyancy, and drag force per unit volume of the particle. Okay. For the flow of a homogeneous mixture of gas and liquid, the superficial liquid velocity can be calculated as volume flow rate of the liquid by cross sectional area of the bed volume flow rate of the liquid by half of the cross sectional area of the bed. Volume flow rate of the liquid by square of the cross sectional area of the bed. None of the above. So the question asks as to determine the superficial liquid velocity, that is u or u naught or ul something, and the given thing is q liquid, it is given, and q liquid is given, and area of the bed it is given. So the question is how we relate volume flow rate of the liquid and the cross sectional area of the bed, or it is either a cross sectional area or half of the cross sectional area or the square of the cross sectional area of the bed. In general, how do we determine the superficial liquid velocity is that we divide the volume flow rate of the liquid by the cross sectional area of the bed. So answer to this problem is option A, that is volumetric flow rate of the liquid divided by the cross sectional area of the bed. Option A is the right answer. Option B and C giving half the cross sectional area of the bed and square of the cross sectional area of the bed, both are wrong. So yeah, answer to this is option question 13. Answer is the right answer is option A. Yeah. Answer is volume flow rate of the liquid by cross sectional area of the bed. So we are determining the velocity of the fluid by calculating the volume flow rate of the liquid divided by the cross sectional area of the bed. So now we'll just go to question 14. Okay, question 14 is a problem where we are asked to calculate the terminal velocity for the sharp irregular sand particles, and okay, data given is density of the gas rho g, it is 1.2 into 10 power minus 3 gram per centimeter cube, and viscosity it is given by 1.8 into 10 power minus 4 gram per centimeter second, and effective particle diameter is given by dp star, it is given by 160 micrometer, and density of solid is given by 2.60 gram per centimeter, and 5s is given by, that is the particle sphericity is given by 0.67. So what is the question is terminal velocity for sharp irregular sand particles. So okay, what are, now we need to determine the terminal velocity of the particles. So actually this can be done by, first we need to identify the terminal velocity and check whether the particles are falling in that regime or not by calculating in turn the diameter of the particles, sorry, particle Reynolds number. First we should calculate the terminal velocity and then cross check with the particle Reynolds number and see if it is within that regime, it is fine, or else we should go again, because for the terminal velocity formula is different for different I think I'll take out one new slide. So actually we are asked to determine the terminal velocity. Ut is given by, for example, consider this as a laminar regime. Qt is given by mm, rho p okay rho p minus rho f rho p minus rho f into g into d dp square divided by 80 18 mu. So on substituting all the values, we would be getting rho p minus rho f. Rho p is 2.60 minus 0.0012. If we are going with gram per centimeter 10 power 3, okay, into 10 power 3. If we are going with SI unit, 10 power 3 into 9.81 into, we need to calculate dp is 160 into 10 power minus 6 square by into okay 1.8 into 10 power it would be 2.6 minus 0.0012 into 10 power 9.81 into 160 into 160. Here we should include 5s, that is sphericity with dp, so it would be 5s into dp square. Since it is given irregular shaped particles, so it is 5s into dp square. 5s. So again it would be 0.67. So the answer is roughly 0.09 meter per second. Now we should check Reynolds number. Rep is given by rho VDP, rho VDP, rho UT dp by mu. So we should get rho is 0.0012 9 into dp is 160 into 10 power minus 6 by mu is 1 point 0012 into 0.09 into 160 divided by 1.8 into 10 power minus 2. Okay, answer is actually 9.6 into 10 power minus 5. So actually from this it can be seen that since REP is less than 1, the regime is laminar regime. So the calculation by using this formula is the right one. So answer is 9 meter per 0.09 meter per 0.09 meter per second. It is roughly closer to 90 centimeter per second or 88 centimeter per second. So the answer to this problem is question 14 is 88 centimeter per second. Yeah. Now we'll just go to next question. According to when and you, a void fraction at the minimum fluidization depends on density of the particles, shape of the particles, volume of the particles, none of the above. So what does void fraction at minimum fluidization condition depends on? We all know that the packing fraction, see, when we are packing up particles inside a bed, when and use used when we are dealing with a dense packing. So the correlation from when and u is used when we are dealing with a dense packing. So the void fraction or the void fraction is proportional, or it is calculated from the packing fraction. Like packing fraction plus void fraction is the one is the should be equal to 1. The volume of the particles, consider the volume of particles and the volume of bed is volume of bed B. So the void fraction is given by we'll keep packing fraction or epsilon. Okay, particle fraction, that is epsilon s, is given by volume of particles inside the bed divided by the total bed volume. This is given by epsilon s, that is the particle fraction, that solid fraction inside the bed, or the particle fraction inside the bed, that is given by volume of particle by the volume of particles by the total volume of the bed. To get the volume void fraction, what we do? We do 1 minus epsilon s. It is equal to 1 minus Vp by Vb. So this, according to Venenu, void fraction at the minimum fluidization depends on, at the minimum fluidization, the particles are suspended in the bed and they have volume, right? So here what are all the parameters? In general, it is affecting volume of particles. Volume of particles, it depends, and also shape of the particles and density of the particles. For example, consider the when and you, it is similar to Ergun equation. So generally, in general, the condition is that for the void fraction, the minimum fluidization. Okay. Okay, just a minute. Shape of the particles is right, but actually it depends on all the three. Answer is not option B. Answer is, it depends on density of the particles also. I'll clarify this question at the end of the session, but answer is it depends actually on all three: density of the particles, shape of the particles, and volume of the particles. So, okay, a white fraction. Yeah, I'll clarify this question at the end of the session. Um, Question 16. Drag force is acting in which direction to the relative motion of any object moving with respect to the surrounding fluid? So, we are having the fluid over here. See, here we are, this is a particle. Okay, this is a particle and we are passing the fluid in this direction. So when we are passing the fluid in that direction, the drag force on the particle acts in the direction, same direction. Okay, okay. The fluid is in this direction. Drag is acting. Fluid is, the particle is here, and we are moving the fluid with velocity this way, and the drag is acting in this direction. But the particles will be moving in this direction. So the relative motion of any object moving with respect to the surrounding fluid would be, particles would be tending to fall down, right? But instead of that, because of the fluid velocity, the drag force would be acting with because of the fluid velocity, and it would be pulling the particles to move upward rather than it falling downward due to the effect of gravity. So the relative motion of the object with respect to the surrounding fluid, the tendency would be to act downward, or the gravitation, because of the gravitational effect. So drag force would be acting in opposite direction to the relative motion of the any object with respect to the surrounding fluid. So the particle motion is falling downwards, and the drag force is in this upward direction. So the answer to this is option B, that is in the opposite direction. And now we'll move to question 7. Okay, when the particle Reynolds number value is 680, the flow is Stokes flow, laminar flow, or the turbulent flow. Uh, we all know that when the particle Reynolds number is exceeding 500 but less than 2 lakh, the flow condition is turbulent flow. So the option answer to this question is option C, that is when the particle Reynolds number value is 680, the flow is turbulent flow. Since it is exceeding the 500 value, the answer is answer is turbulent regime. Stokes flow or laminar flow occurs when the Reynolds number, particle Reynolds number REP is less than 1. REP is nothing but rho V dP by mu, where rho is the density of the fluid and V is the particle, I mean fluid velocity, and dP is the diameter of the particle, by mu, that is the viscosity of the fluid. So answer to this is turbulent flow. And we'll move to question 18. This is a similar question. At minimum fluidization velocity, the weight of the particle is just counterbalanced by the frictional force between the particle and the fluid, gravitational force acting on the particle, buoyancy force acting on the particle, none of the above. So at the minimum fluidization velocity, the minimum weight of the particle is counterbalanced by the gravitational pull, like frictional force between the particle and the fluid. Like when fluid is passed into the bed, because of the fluid motion, the particles and the surrounding fluid, there would be frictional force. This is known as the drag force. So at this drag force, the weight of the particle is just counterbalanced by the frictional force between the particles and the fluid. So answer to this is option A. At minimum fluidization velocity, the weight of the particle is just counterbalanced by the frictional force between the particles and the fluid. Now we'll go to question 19. Distributor hole diameter which can affect the minimum fluidization velocity is categorized as thermodynamic variable, geometric variable, variable as a thermodynamic variable, geometric variable, variable as physical property. And it is nothing but when we are dealing with the distributor hole diameter, that is when we are passing the fluid inside the bed, we would not be passing it through directly. We would be having distributor plates that would be form of different designs would be there, and the distributor hole diameter here, since it is based on the geometry of the pack and the of the bed, it is known as geometric variable which can affect the minimum fluidization velocity, is categorized as geometric variable. It is not a thermodynamic variable or a physical property. It is geometric variable since it is the like fluid would be passed through the distributor plate, and the distributor hole would be having the diameter which should be affecting the minimum fluidization condition or the minimum fluidization velocity. So this is categorized as geometric variable. So answer to this question 19 is geometric variable. And okay, a fluidized bed is operating with air. Okay, this question is an incomplete question actually. But for cubes, the packing fraction is around 0.6. So at the okay, a minimum fluidized bed is operating with air at minimum fluidized condition with the particles of cube 0.02 meter side. The void fraction of the bed is uh, actually this is an incomplete question. We cannot calculate the minimum void fraction with this data, but in general the packing fraction of the cube is 0.4, that is I mean 0.6. So the void fraction at the packed condition or the tightly packed condition is 0.4. We all know that with at minimum fluidized condition the void fraction would be slightly more than the uh, than that at the packed bed. So it is it would not be like, since 0.4 is the condition at the closed packing, it would be more than 0.4. So answer to this is option A, that is 0.45. 0.45 is the void fraction at the minimum fluidized condition. It is, we should note that it is at the minimum fluidized condition for the cubes of side 0.02 meters. Since it is for the cubes, we are taking the value from the literature as 0.4 and we are further making the calculations. So yeah, thank you. Before ending the session, I'll just give the, there was one question with doubt, right? I'll just clarify that and then we'll end the session. Just give me a minute. I'll check with, I'll check and get back to you. Just give me a minute. Okay, actually, white fraction to minimum fluid fraction. I guess it is given based on according to when a new white fraction, it is calculated for the shape of the particles. Like, okay, just a minute, I'll just go through the paper and then confirm. Okay, actually, when and you has given a correlation between a graph where it is given that dp is given over here, that is the diameter of the particle, and in the y-axis they have given phi s square, phi s cube, epsilon mf cube by 1 minus epsilon mf square. So, according to their correlation, in order to get the epsilon mf, we need to know the phi s and the dp. So, the question is here is according to Wen and Yu 1966, a white fraction of the minimum fluidization depends on. So, in this it depends on the phi s and the dp. So, phi s is the shape of the particles, that is it is a sphericity of the particles, and so density of the particles and the volume of the particles are not accounted here. So, uh, based on this, copy. Uh, like according to Wen and Yu correlation or Wen and Yu, the white fraction calculation is depending on this shape of the particles and not on density or the volume. It also depends on the size of the particles. That is a different thing. So in general, according to Wen and Yu, to calculate the white fraction, it depends on the shape of the particle. That is, here it is given by sphericity of the particles. So that is the answer, option B. So option B here is the right answer. So that these are all the problems for this week session. If you have any doubts, you can ask. And some actually one person, yeah, if you have any doubts, you can ask. You
Yeah,
asked
could you
for
like
the,
upload these videos?
yeah, I'll give the link for the last week.
Thank
I'll
you.
put it in the chat box. Can you just see if it works? No, I'm not. I'll just give me a minute. I'll put. Uh, Can you just check if this link works?
Yeah, just give me a second.
Yeah.
Yeah, yeah, it's working. Thank you.
Yeah, yeah. And this week one also would be uploaded in the same thing. You can see actually NPTEL would again send you these. Maybe it would take some time
Ah,
for them. Yeah, but all these videos would be uploaded in the same channel. You can check that. Yeah.
okay, so all of these recorded sessions of all NPTEL courses will be on YouTube, is it?
I mean, for the problem solving sessions, they will be uploaded in the YouTube. Yeah.
Okay, thank you.
Yeah. Sure. That's all for today's session. If you have any doubts, you can ask, or that's it.
Yeah.
Okay. Thank you. Thank you for attending. Yeah. Thank you for attending. Actually, the sessions will be from 6 p.m. to 8 p.m. every Friday uh, for the duration of the course. So we'll meet again next week at the same time. Next week, same time, from 6 p.m. to 8 p.m. So for today's session, we will be closing it shortly. Uh, Thanks everyone. We covered about the fluidization phenomena, advantages, disadvantages, and industrial applications, and the few problems associated with the course. So for this week course, the we have discussed the problems, and next week we'll come back again with a few set of problems uh, regarding the next week. Next week syllabus are covered in the next week. So thank you. The main content for the course is in the NPTEL website, which is provided by the professor. Uh, so these are just aids to help you in understanding the assignment problems better by providing few sample problems. So if you have any questions, you can give it over here. You can attend the session and ask them during the session. In the during the session or after the session, anything would be fine. Please feel free to ask. And thank you. I thank everyone for attending today's session. Okay, thank you.